Okay, I would like to go over briefly the material for this week, sections 2.4 through 2.7. First is derivative of sine and cosine. Now you may remember what these are from your calculus class. Derivative of sine is cosine, and derivative of cosine is minus sine. How do you remember that the derivative of sine is plus cosine and derivative of cosine is minus sine? Well, think about sine. When sine is near zero, sine goes up. So the slope is positive, so the derivative is positive. So the derivative of sine must be positive cosine. On the other hand, cosine, when cosine of zero, as you increase the angle from zero positive, the cosine decreases, right? So that means the derivative becomes negative. So derivative of cosine is minus sine. Now, how do you originally derive the derivatives of sine and cosine? Well, you use the limit formula, and it's good to remember that what you actually need to use are the angle addition formulas, and these limits that have been computed before, cos minus 1 over h and sine h over h. These are limits that we've looked at before, and that's how you define the derivatives. Okay. So one thing he likes to say is that cosine h minus 1 is like, cos h minus 1 behaves something like h squared. So, and you take the limit as h goes to 0, h squared over h is going to go to 0. Of course, that's 0 over 0, but you can say this 0 is smaller than that 0. What you do is you take h's that are small, like h equals 0.01, then this becomes 0.0001, and this is 0.01. So that becomes very, very small. Of course, h squared over h is the same as h, which goes to 0 when h goes to 0. All right, so they have this kind of stuff. Okay. And here he goes over the fact that sine h over h is 1. I think we had an exercise about that. And once you have that limit, you can find this limit of cos h minus 1 over h is 0. So what he does is he uses this trigonometric identity and replaces sine h with 1 minus cosine squared. Okay. So we have this here, sine h squared is less than h squared. So we can get we just basically rearrange this identity. 1 minus cosine squared equals sine squared, and use the fact that sine squared h is less than h squared. Rearrange that and you get this identity, and then you take the limit as h goes to 0. Now, of course, when h goes to 0, this numerator goes to 0, this denominator does not go to 0. So here we have a numerator which is 0 over non-zero, which is definitely a 0 limit. So what's in the middle here is 0. So this is called a squeeze argument. He does the same thing for cosine. Then he talks about second derivative. Second derivative is the derivative of the derivative. There's really nothing new here. Now what's important here is to be able to identify graphically what the second derivative is referring to. If we look, for example, at this curve here. If I look down here at this dotted curve, what can I tell about the second derivative? Well, the slope here is negative. The slope is negative, but it's becoming less and less negative, right? It's becoming less steep. So the derivative is changing in a positive direction. Second derivative is positive. Same thing here. If I look at this solid curve, I can see the derivative is positive because I'm sloping upwards, but I'm getting less and less steep. So the second derivative is negative. All right. If I wanted a case where the derivative was positive and the second derivative was positive, you could think of a parabola, x squared. Right? In that case, the slope is increasing. The slope is positive and increasing. That's like an acceleration. All right. Or if you wanted a case where the derivative and the second derivative were both negative, you'd have a parabola going down. So ideally, given a graph, you should be able to sketch the derivative and the second derivative of the given function. for example, here I sketch this function here. This is f of x. Now suppose I want to sketch f prime and f double prime. All right, this is something you should be able to do. All right, so let's go ahead and sketch these. Well, first of all, let me identify some points here that are important. If you want to identify important points, first you should identify minima and maxima. Okay, so here I have a minimum. Let's make this a different color here. This is a minimum here. Now this one is not quite a maximum because it doesn't go up and down. You see it keeps increasing but slowly, so it's not a maximum. This is a maximum here. And then here's a minimum. So those are the maxes and the mins. So let me call this point, I'll call this point A, and I'll call this point B, and I'll call this point C. Now the other important quantity is the points of inflection. That's when the concavity changes. So you should be able to identify points of inflection. Now there's one here. It may not necessarily be on the axis, but it's close. You can see that here it's concave up, and here it's concave down. Here's another point of inflection. All right, here it's concave down, now it's concave up. Here's another point of inflection. It's concave up, then concave down. Here's another point of inflection, concave down, then concave up. And those are all the points of inflection. So let me call that A prime, B prime, C prime, and D prime. Okay, so let me redraw my axes down here, and I'll do the plot of f prime. Something very necessary that you need to be able to do to understand how the derivatives work. All right, so here's my plot of f prime of x. All right, so let me plot my points A, B, and C. A is here, B is here, C is here. All right, now we know that the derivative is 0 at these places here. So I'll make my derivative in green. Okay. So the derivative is actually going to be 0 at these 3 points. Now what about in between? Well, here you can see it's increasing until it reaches here. So the derivative is going to be positive up here. There's going to be some wiggles here, but let's well, all right, so let's look at the wiggles here. All right, so let me go ahead and mark in my points A prime, B prime, and C prime. A prime, B prime, and C prime. Okay, and then here I have D prime. All right, now, all right, so what happens to the graph at these points? Well, here we know that the second derivative at an inflection point is 0. So that means that the derivative of this function will be 0 here. Not the function, but the derivative. What does that mean? That means that the function is flat. The function is flat. Okay, so I'm going to have a max or a min here. I'm going to have a max or a min here. And I'm going to have a max or a min here. So since the derivative is getting bigger and then smaller, this must be a maximum. So that means that the derivative, whoops, I was going to make it in green, so let's go ahead and make it in green. The derivative is becoming bigger, max here, and then smaller. All right, now B is going to be a minimum. In fact, the derivative here is very close to 0. So it's going to come down and be like this. Right. Then here I have another maximum. I can't really compare this one and this one. Maybe it's a little bit higher. And then it goes down to 0. Okay. Now here what do I have? Here I know that the derivative of the derivative is 0. But the derivative itself is highly negative. So what we have here is a minimum like that. So that's my f prime. All right, let's look at my f double prime. Well, I could look at my f prime and take the derivative of that. or I could take my f double prime directly from my original graph. Let me try to get my f double prime from my original graph directly. Okay, so I'll make it down here. Actually, why don't I do it on the same axes here? I'll just use purple for my second derivative. All right, so what do I know? I know the second derivative is 0 here, 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 and here. So I have 0 here, 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 and here. All right. Now here you can see the second derivative is negative. Why? Because it's concave down. All right. Here the derivative is negative, and it's the derivative is positive here, and it's decreasing. Here it's very steep, here it's less steep. All right? So that means that my second derivative is negative. It's negative from here to here. So that's going to give me a negative second derivative, which looks like this. All right? From b prime to c prime, what do I have? Second derivative here is 0, because there's an inflection point. Second derivative here is 0. But what's the second derivative doing in between? Well, here the slope is not very steep. It's becoming steeper and steeper. So here the second derivative is positive. Looks like that. Okay? All right, how about from c prime to d prime? Well, what's happening? Here the slope is positive, and it's getting less and less steep, turns around and becomes negative. Now the turnaround doesn't matter for the second derivative. In fact, the second derivative is more or less is always negative here. So we have something like this. Okay, so that's my f double prime of x. All right. Now, where are the inflection points of the second derivative? I don't really know, but I do have the general shape of the second derivative. All right, so let's see, from a to a prime, I should finish this. Well, here, let's see. We're going to have another inflection point over here somewhere, but we haven't reached it yet. What about the second derivative here? Well, the derivative is increasing, so the second derivative is positive like this. All right. So here you can say the relationship between derivative, second derivative, and the original function. And we'll be doing more problems like this later. I really do want to emphasize intuition and visualization in this class. Very necessary to understand these things when you're doing calculus. All right, let's go back to our PDF, which is here. Okay. All right, so here he talks about the significance of derivative and second derivative. Second derivative is greater than 0 means concave up, like a upward bowl. Second derivative less than 0, concave down, like a negative bowl. Right? So here we have the second derivative. Well, what about second derivative of cosine? It turns out derivative of cosine is minus sine. Derivative of minus sine is minus cosine. So the second derivative of cosine is minus cosine. Similarly, second derivative of sine is minus sine. So it's interesting that both cosine and sine satisfy this equation. The second derivative of cosine is minus cosine. So if I put y equals cosine in this function, I get d squared of cos squared of cosine, dt squared, is minus cosine. The same thing happens with sine. D squared of sine, dt squared, is minus sine. All right? So in fact, any combination of sine and cosine is a solution to this equation. This is extremely important in physics, and it's one of the reasons why so many phenomena that we see oscillate. Like it talks about bouncing balls or waves or all kinds of stuff that oscillates, heart rhythms and so on. The basic reason is this. It has to do with the second derivative giving me a minus here. The second derivative of the function is minus the function. Very important. If you remember Newton's law, F equals ma. A is a second derivative. So second derivatives are extremely important in physics. All right? So that's good for 2.4. I'll make my next video on 2.5.